7.3, electromagnetic spectrum. Yes, I have a new pen. You can see now. Work, number 1 AB and number 2 AB. Okay, so for AP students, I probably put these, you're having to do 2 in a row, 2 lessons. But anyway, this should be a shorter, a little bit easier one. And I talked a lot about this in the last lesson. So if you don't know what I'm talking about, General Chem, for example, you do lesson 7.2 one day and then 7.3 the next day. But AP has to do both of them, but they have a little bit less work to do because we have to cover more material in there, which we got to really get going. But this is not so bad, and I talked about a lot of it. All right. So I already mentioned to you electromagnetic radiation and radiant energy. They're the same thing. And there are, I don't know how many of these, 1, 2, 3, 4, 5, 6, 1, 2, 3, about 6 types on here of common electromagnetic radiation. 6 types of common radiant energy are on this page. And you ought to know this. You ought to just kind of know it by memory. It's not a bad idea to know. I'll show you why. So this is, on this far end of it would be radio waves. Actually, when we say radio waves, really, radio waves and TV waves and even cell phone waves are in that area. Cell phone is a little bit to the right, though, if you want to put cell waves. But anyway, I'm adding that in. It's not on the paper. But radio waves are on the far left. On the far right, you have gamma rays. Now, it's not really in the middle mathematically. I've got some numbers up there. Let's just see. The far left is 10 to the third. That's wavelength, okay? And the far right, 10 to the negative 12. And in the middle, I put visible light around 10 to the negative. Actually, it's negative 7. I don't know. Close to 10 to the negative 7 to negative 8. So yeah, it's not quite in the middle. I'm just kind of talking to myself. Here I'm going crazy. But visible light will be somewhere here. We normally put it in the middle. Visible light, it's a little bit closer. It's closer to this end, actually. I didn't do a good job. I guess I could make gamma ray move over here. Gamma ray over here. Oh, no. So, sorry. About where it was. I need a little bit of space. That's why. Radio wave, visible light, gamma ray. Now, right above visible light, you have ultraviolet. So I'll put UV light. Okay, and then above that, on the left of it, you have infrared, IR. Above ultraviolet, you have X-ray radiation. And below infrared, you have microwaves. Now look at this. For micro, I'm going to put mu. Can you remember micrometer, mu meter? Mu waves, microwaves. A little short way to do it. Now, so what are these things? Again, this is energy, pure energy that travels throughout space in the form of waves. That radiates out like waves do. Like I told you before, from a little tower or whatever, it goes out in these pulses. Like when you drop a pebble into the water or whatever, but they're going like 3-dimensionally. Like imagine like a basketball. Not just you drop it down into a pond and you see the circles grow. But imagine if they're coming out towards you in every way like this, like a basketball growing and then another one. That's what it would be like. Okay, so like radio waves, you could think of it. If you want to, you can think of them as radio waves. I mean, they call them all these radio waves, but cell phone radio waves, visible light radio waves, X-ray radio waves. Okay, what they're rays. That probably is the best way to call all of this. These are all rays. Microwave rays, visible light rays, gamma rays, cell phone rays. I think I might like the word ray a lot better. Oh well, here we go. All right. Now, why do you need to know this? Well, it's a good idea to have it memorized. Now, to know this, because on this side, you have very long... I don't want to draw the words. I want to draw a picture. That's why I need a little space. Oh, no. Okay, on this side, I'm going to draw something like this. All right? But on this side, I'm going to draw... I don't have as much space, but it won't matter. Like that. So, can you see what I've done there? Oh, that one is so small. Well, I can do it again. All right. Just because of the video, I guess. Well, I didn't do too good of a job there even, but oh well. Anyway, here's the point. So on this side, how is your wavelength down here? And what is the symbol for wavelength? It is lambda. Well, wavelength lambda is long. You have long wavelength over here. You know that because look, just connect from here to there. That's a long wavelength, but take two there, and that's a short wavelength right there. Short wavelength here. Can you see that okay on the video on the screen? I don't know. I see light. It's actually kind of sunshiny right now. Yeah, maybe you can see a little bit. Short wavelength, long wavelength. Now, frequency. The frequency on this side will be high or low frequency. Well, like almost like 1.5 really. It didn't quite do the whole picture. About 2 hertz. This one I got about 3. So here it's a greater frequency. So here's a low frequency. So long wavelength. I like to write it that way, I guess. Low frequency. And frequency, the symbol is the V-looking thing. Frequency. Here you have a short wavelength, short lambda, and a high frequency. Okay, so it's good. You need to know this. I'm telling you, you all need to know. You'll see why in a minute. So this hat has a long wavelength. This hat has a short wavelength. This is a low frequency. This is a high frequency. So the picture actually tells you, like if you see, all right, if that's a low frequency and a long wavelength, that will be a high frequency and a short wavelength. Now, of course, that would be in the same amount of time, 3 waves, almost 3 waves, or whatever it was, 6 waves. That's a better picture there. So, tell me this. If you have a long wavelength and low frequency, or if you have short wavelength and high frequency, which one do you think has more energy? Now, when I say more energy, it's like saying, when you get on a treadmill, you're doing exercise on a treadmill, it'll say you've been walking for like 10 minutes or whatever, you're pushing the thing below. You have to do work on that. You actually, that really is, your feet actually have to move the treadmill. And you see, okay, it says I burned 50 calories, or whatever you did for 15 minutes or whatever it was. 50 calories are burned. Okay, that means it took 50 calories in you from your food, from your energy, burning it off, stored up chemically. 50 calories of energy, so you can do 50 calories of work. All right? Well, which one of these have more energy? In calories or in joules? We use the word joule, okay? So which one has more? Do you think this one or this one? It almost looks like from the frequency, like the impulses. Here they're like this, the frequency, every second. But here they're like 3 ways, or I don't think I can even hit that many a second. Okay, so obviously that's a higher energy. I mean, that's just one way to think about it. The high frequency means higher energy. So short wavelength, high frequency, high energy, and we'll talk about that in a minute. And this will be low energy, lower energy. So all lower energy and higher energy of what we call a photon. I'm going to talk about that in a minute. So, but there's a little bit more on this spectrum you need to know. So first you need to know pretty much, I don't think you're going to see too many questions about that, but you should certainly know that gamma rays and X-rays, I guess you need to know that ultraviolet is higher, has more energy than say visible light. You need to know as you go this way, you're increasing. So going this way, you're getting to a longer wavelength, and going this way, you get to a shorter wavelength, okay? So short wavelength, long wavelength. And then, of course, that will be low frequency and high frequency. I guess I can't write it all down. I kind of wrote it there. All right, but you also need to know about light. But before I tell you about light, let me just quickly tell you about these things. You know what radio and cell waves are. It might be interesting to think, well, microwaves are low energy compared to even light. Remember, visible light, the visible light, we would call it white light, but then that can be broken down into And we say broken down. The scientists knew this a while back too, that like having a prism or like a piece of glass, and you shine white light through it, or like a magnifying glass at a certain angle, it bends the light rays, and you see that what we think is white light from the sun is really made of the rainbow. Roy G. Biv is how they name it a lot of times. Even, water droplets can do that as well. That's how we see a rainbow. But Roy G. Biv. Now, Newton decided to name that Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Because he had some sort of a theory thinking that that like the same way that musical notes in a scale are like do, re, mi, fa, sol, la, ti, and then you start with do again. So there's 7 notes before you go to an octave to go to the next one up. So he thought that there would be like 7 main colors. I don't know if it was just an idea or just whatever. Because he was brilliant, amazing scientist. But really, this is more arbitrary, as I mentioned. It's just, what is red? Well, red is just something with a longer wavelength than orange. But sometimes I can show you something, a color, and you say, oh, it's red. But then next to it, I can put another color, and you say, oh, well, I guess that isn't red. That might be orange. Okay, so it's more orange than red. So there's like, the Crayola mega packs that have like red, brick red. You may have seen cobalt red before. That's one I can actually show you. That might be an old, may not use that term as much. Brick red, cobalt red, crimson red, or blood red. They wouldn't say that on crayons. That will scare the kids. Orange red. Have you seen that? There's orange red or red orange. Well, okay. Well, anyway, you can have many different colors to add in there. Magenta, violet, and there's a purple, and there could be. So there's a whole lot of things. Blue, turquoise. So you know that an actual spectrum, there are probably millions of little colors you can see. If you can blow a giant poster of a rainbow up and look at all the colors, you can see many blending. But what's interesting is, though I say there might be millions of colors, there are, according to the quantum theory in Einstein, there's a limited number of colors. So it might be somewhere in the millions, but there's a limited number of colors. Very interesting, because of the particle theory of energy. So, all right, but back to this again. All right, so you need to know that red light has a longer wavelength than green light. Okay, or the wavelength of violet is very shorter than the wavelength of blue light. Okay, you need to know that. Or that violet has a higher energy, photon energy, higher energy than does a red light photon. Now, what do I mean by photon? I'm going to get to that next. Violet has a higher frequency than green light. Green has a lower frequency than blue light. So you should know little questions like that, what is a longer wavelength, especially for Roy G. Biv. Maybe even for some of the other things that you see in there. All right, so here we go. So there you got Roy G. Biv, and we'll come back to that. So back to the photon. So the scientist's name was Maxwell Planck, P-L-A-N-K, and there he is, Maxwell Planck. He can look right there at you. And you see that it says in 1900, he says, he studied the radiation that was emitted from solids when they were heated, called black body radiation. There were 3 amazing experiments that were done. One was, there were questions, there were puzzles. Actually, I should say it that way. There were 3 big puzzles. One of them was called black body radiation. One of them was called the line emission spectrum. That's the one we're talking about. And another one was called the photoelectric effect. The photoelectric effect, all 3 of these things were puzzles that scientists could not understand what is going on here in the early 1900s. And Einstein won the Nobel Prize for answering one of those questions. What is the photoelectric effect? But it is absolutely, I'll do a video, I'll do something on that lesson. But it is amazing because the answers to those questions, it shook all of science, all of what Newtonian physics, and it was the beginning of quantum physics. They realized something is going on, that something else is happening at the small particle level, the subatomic electron level. Something is happening that does not match the reality that we know in our everyday life. See, think about this. You know, we're bodies, we're masses. We walk around, material. You know, we walk around in the world, matter, material matter, and all that. How fast we can run. There's a whole lot of physics we can do with that. You know, we can take a like an object, like well, I better not. I would be careful not to drop anything too much. But like, I can take this little ball, and we can already tell you right now that if I let go of that to drop it, I can tell you that right now its speed is 0. But I can tell you exactly what its speed was there, and there, as gravity speeds it up. I can tell you all of that in physics. I mean, everything can be done. We can make all these predictions about speed, where it's going to be. Well, all of those things, if this were an electron, those rules don't work. Because electrons are, it's like they're moving so fast, they have a different sort of existence. If we could be existing the way the electrons and those small particles, if we obeyed the laws of physics for electrons, not for us, then we would be doing things like traveling through space and time. Like, you can beam a person up from here to, let's just say, to the moon in a second. You know, the idea is here your energy, here your mass, your matter, like you're saying, beam me up. Then you turn into energy, light, and then as quick as light, you can be to the moon, and then you'd rematerialize there. Or you could go from here to the sun in, what does it take? It's like 7 minutes or something like that for the however long it takes for the light from the sun, 7 or 8 minutes to get to the earth. That's how long you can get to the sun. If you could have a wave turn into a wave, electromagnetic energy existence. And that is a bizarre, strange thing. And you've seen that in this equation before. Energy, the crazy thing is that energy, when Einstein talks about energy, he's talking about this kind of energy. Electromagnetic wave energy. Rays are equal to the amount of mass that you have, kilograms. All you do is you multiply it by the speed of light squared. And the speed of light, we saw that before, 3 times 10 to the 8 meters per second. So what he was saying is that energy and matter and energy are interchangeable. You can change mass into energy or energy into mass. That appears to be going on at the level of electrons. The electrons are particles, but the way they're moving, they take on what they call a wave nature, an energy, a radiant energy nature. It's like saying that, you know, could we turn you into like a radio wave, and people, you know, you could pick it up on a radio and then rematerialize yourself there or something. But okay, very strange. So all of science fiction, think about science fiction. Most science fiction started in, I believe, like the early 1900s, 1900 to 1920. A lot of science fiction was written and made then. And many things that were fiction in science fiction have come true now. Kind of bizarre, kind of amazing. Now we're not able to beam me up to somewhere else and all that. But still, there's a lot of science fiction is based on science, but we don't have the technology. And sometimes it might break science. But I once saw a neat website that they listed like all the things in science fiction that have come true. And there were like, I think there were like 7 or 8 things this person had listed. But then there's a whole lot of other stuff that hasn't. And I don't know, will we ever get the technology? Or could we be wrong about some of those other things that haven't come true? But still, pretty amazing. You know, like even like, well, I'll just throw in there, you know, that you've probably heard before, like say if you could travel for 1 hour at the speed of light. We don't have a technology that could do that. Ships or rockets or jets could withstand that. Not now, not yet. But if you could travel for like an hour, then when you know, for you it would be 1 hour. When you arrive, okay, 2 o'clock, I arrive at 3 o'clock. But when you touch down at 3 o'clock and you come back, you know, say you circle around the Earth or whatever, you come back and you land an hour later, going the speed of light for an hour. When you land on Earth, it will be like 30 years later. I don't know if you've ever heard of that before. Pretty amazing. And Einstein mathematically proved that. It's really incredible. So you would be skipping, because you would be taking on a wave nature, and you'd be skipping through space, and for that matter, skipping through space and time. So, okay, there's some neat stuff, and I would love to talk about this forever and go on. It's really interesting. It's really cool, the science fiction stuff, but let's just come back down to Earth now. Okay, so but still, we're going to be going down, not just down to Earth, but down to the electron level. Okay, so Planck, this equation is what he's credited for. The energy of a photon is equal to Planck's constant. I say Planck, but it's probably Planck is the correct German pronunciation. But it's 6.626 10 to the negative 34 joule dot s. This is a constant, just like the speed of light is a constant. 3 times 10 to the 8 meter per second. All right, so here's what Planck figured out, and I got to get to Einstein as well. Einstein, from what I know, from what I've heard, if I'm right, he actually created the word photon. He created the word photon, and a photon is a particle of radiant energy, a particle of energy. Now, see, I mentioned in the last lesson, everything in this room right now is either matter, it has mass, takes up space, and hey, for chemistry students, we were all chemistry, matter, everything in the room that is made of these things, that is made up of this stuff, anything that is made of any of this is matter, okay? So the air has oxygen, carbon dioxide, even some water vapor, nitrogen is like the number one gas, helium, this, chalk does. Chalk has CaCO3, calcium carbonate. I mean, got a lot of things. Everything, things that are made of steel in the room. Like I think I showed you this one was made of iron, steel, a little ball there, ball bearing. So everything you can touch is made of something on this chart. That would be matter. But there's other stuff in this room right now that cannot be found on the chart, and that would be energy. That would be like the radio waves, hundreds of radio station waves, cell phone waves, internet, Wi-Fi from everybody, all of your neighbors, everybody, all of this, or all around you, all of that, Wi-Fi, all of that would be on this list. So Einstein was saying, no, there's a particle nature of those. Kind of strange. A particle of red light, or a photon of red light, a photon of green light. Again, in science fiction, a lot of people use that photon, or you hear photon torpedoes, or you see like a spaceship shooting this like a laser little blast out, and they call it a photon. Well, the idea of a photon is actually that. Instead of just having a continuous ray of light, when the sunshine shines on you, a ray of light comes on you, and I get some more lighting up, it's daytime, okay, light comes in, well, it's actually particles of light are coming through. Particles of light. What in the world is that? That's what Einstein showed. So we operate in science saying that the energy has a wave-like nature and a particle-like nature. Okay, so here we go. So the particle, a particle of an X-ray particle, and there are different kinds of X-rays. Oh, by the way, I didn't even tell you this. I just wanted to mention quickly. X-rays. Well, all right. You know what? The X-rays obviously can shoot through, and they can expose on film. They can expose a light. Light is shot through, X-ray light, like through your hand, and then some of it is absorbed and blocked by your hand, and then an image is put onto a board, and so like the shadow of the light goes through. We'll just say that, and some goes all the way through, and some is blocked or slowed down or whatever we'll say, and you get an image behind it. Well, X-rays are created whenever electricity hits a metal. So if electricity strikes a metal, then X-rays are given off. I think I talked about this in an earlier lesson last semester, chapter 3 actually. So every metal gives off different X-rays. So how you have different colors of light in the spectrum? Well, there's a spectrum for there's an X-ray spectrum as well. Okay, gamma radiation occurs anytime that there's a nuclear change. Anytime there's a nuclear reaction, like in a nuclear power plant, or sadly, if there was a nuclear explosion, like a bomb, it gives off gamma radiation. But where there are another place where most gamma radiation occurs is on stars. Because, on stars, like on the sun, in fact, it's continuous nuclear reactions given off, and all this radiation comes out. But all the gamma rays, gamma radiation, imagine them as being millions of times, probably billions of times more powerful than an X-ray. So think what an X-ray does. You go to the dentist, they put that giant lead thing on your chest, and they walk back behind it. I'm getting out of here. I'm getting behind this big, giant, thick wall. And just to turn it on for like one little bzz, okay, bzz, bzz, then they come out. That quick little bzz, bzz, and they better be blocked by all this stuff. And they put that chain. They don't want to be near it. So X-rays, you think about how bad that could be, having too much X-ray exposure. Well, this will be millions of times what an X-ray is. Really, really bad. But the sun, they're constantly undergoing nuclear reactions. Atoms are squeezing into other atoms and making new atoms, and gamma rays are released. But this is all blocked by our atmosphere. Okay, ultraviolet. Think of it as being light, but it's invisible light. And also infrared is invisible light as well. But this is a higher. You know that UV light can do damage, so we know that obviously it's not as bad as X-rays, but it's more higher energy than visible light. Okay, and infrared is lower energy, and you know that some animals like like snakes, they can see infrared light. Isn't that right? They can detect that. Infrared can be given off as one theory is that saying that in your body, as your bloodstream moves around, you have you have ions in your blood, but as your blood pumps through your body, it gives off rays. You give off infrared radiation. And there's some commercials from like Gatorade. You can always find them online. They'll show like heat sensitive, and they'll show like, you exercise and more red, and then blue like cooler, or yellow or orange in between there, depending on your temperature. Well, how fast your heart and your blood is circulating through you, you give off, according to your temperature, you give off infrared radiation, heat, okay, as heat. And that's how, and snakes can see the infrared. So they're blind, but they can sense the heat of you, infrared. Microwaves, this is interesting. Microwaves, you might say, well, they're low energy compared, I think I mentioned that, didn't answer it. Microwaves, an interesting thing about them is they cause vibration of water molecules. They cause it's like specifically water molecules. So in a microwave, if you put a piece of paper, like a paper towel, a dry paper towel in the microwave, and you heat it for like an hour or 20 minutes or whatever, 10 minutes, 5 minutes, take it out, that towel is not one bit hot, not a bit, because there's no water in it. Now, if you wet the paper towel and do it, well then yeah, it'll be scalding, okay? Anything with water molecules in it, it will heat up. Anything that doesn't have water molecules in it, it will not be able to heat up. And then the cell phone. I just wanted to mention what those were. Okay, so here we go. Calculating the energy of a photon. So, I don't want to erase that. I'm going to use it. I'll just show you the math is just like last time. Long lesson. Lots of things I'm telling you. Long talking. But the math is going to be very easy. And here we go. Under the Einsteins, it says, and there was Einstein, I was talking about him and EMC squared as well. A photon of light has an energy of 3.91, 10 to the negative 18 joules. So, 3.91 times 10 to the negative 18 joules is the energy of a photon of light. Determine A, the frequency of the light. The frequency. So, to find the frequency, guess what? I already got it in there. E equals HV. 6.626. This is a constant that you will be given. Remember, so far you have R, the gas constant. You learned, 0.0821. You learned about pi, the constant, in math class. We don't really use it in chem that much. Then now you know C, the speed of light constant, 3 times 10 to the 8 meter per second. And now H, Planck's constant. So there's a lot of constants, okay? So I don't know. The frequency is like the V looking thing. So then I'll just do the math. So divide both sides by 6.626, 10 to the negative 34. So you have to admit, so far, I told you there wasn't a lot of math in this chapter, but look at the math that we do have. Isn't this like, wow, how easy this is? Just divide, okay, 3.91, 10 to the 18th negative, divided by 6.626, 10 to the negative 34. It's 5.91. Times 10 to the 15th equal, and that will, the unit, I didn't write my units down. Okay, I divide by J dot S and J dot S. If you want to show it, you don't really have to show me this, but the joules and the joules go, and so you have S negative 1 again, which means, just remember, or if you're in general, just anybody, you could even do it in AP, you can just say HZ. Your frequency is 5.91, 10 to the 15th, HZ. You don't have, or if you want to leave it S negative 1, you can do that too. 5.91. Sometimes on the answer key to AP questions, they'll leave it in S-1, but of course Hertz is the preferred unit. So 5.91, oh, I was going to double check my math. 3.91 10 to the 18 negative, divided by 6.626 10 to the 34 negative, 5.91, yeah, okay. Now, that's the first thing, find the frequency. Then B says, find the wavelength and the color of the light. Oh, goodness. I just realized that, okay, yeah, B, the wavelength and the color of the light. So 5.91, right, the wavelength, to find the wavelength, I'll use this equation. So I'll just say, well, what is the wavelength if I know the frequency is 5.91 times 10 to the 15th hertz equals, now put in C, 3 times 10 to the 8th meter per second. So the same one that we saw from the last lesson. So now, just divide both sides by 5.91, 10 to the 15th, 5.91, 10 to the 15th. And if you wanted to, you could even put S-1 for your unit, because that is the same as S-1. Just to show that that'll take away the S and your answer will be in meters. I mean, if you really want to show the details of that. But all it will be is 3 times 10 to the 8th divided by 5.91 10 to the 15th. Oh, sorry about that. And it's 5.08 10 to the negative 8. Now, the bad thing, I can tell you this right now, the color of the light, when I made this worksheet, I need to change it one day. When I made this sample, this light, unfortunately, would be invisible. But if you look on a spectrum, it will actually tell you, even for Roy G. Biv, what we call red, orange, yellow, green, blue, indigo, violet, it will tell you what the number is for each color of light. Like 10 to the negative 7. It's usually around 10 to the negative 7 range. Like, you know, I think it's like just like 4 times 10 to the negative 7 up to, like, I don't know, 7 times 10 to the negative 7, somewhere in that area, 4, 5, 6, 7. Well, anyway, not negative 8. That would be like invisible. So I can't tell you the color of that. But now there's one more thing, C. Now that was B. I didn't label these. A was, we did that equation. B is this one, and now C is only something that that you need to know. For only the AP students need to know this one. And you know what? When I told you the homework at the very beginning, did I tell you the homework? I said only do one A, B, 2. No, AP, you do need to do one other. You need to do the one with the what I'm going to show you right now as well. I'll try to see if I can find it. But if not, okay, all you do, this is just for AP only. Yeah. Oh, no, AB. Oh, no. Energy in kilojoules. What frequency? Well, you know what? This is for AP, but it doesn't come on this assignment. It's going to come on a later assignment, but I want to show you how to do it real quick. Okay, so here we go. It just says, calculate the energy in kilojoules per mole of a mole of photons of this light. Okay, here's the deal. In the very beginning of the question, it says this. This has to do with thermo, actually, in quantum thermo, if we call it that. 3.91 times 10 to the negative, this is actually going to be easy, 10 to the negative 18 joules. Okay, this is how many joules of energy you get for a one photon. So it's really better to say joules per photon. In fact, E equals HV, energy, if it were put the word photon, to add that word, the energy per photon. This is how much energy for one particle of energy. If I wanted to change that to what we saw back in the thermo chapter into kilojoules per mole, here's how you do it. First, to change joule to kilojoule is simple. Joule, kilojoule, 1 kilojoule is 1,000 joules. So you just divide by 1,000. But now I want to change photon to moles of photons. And this is an easy thing to do. But remember, photon, instead of having photon, I want to put mole there. That means that I've got to cancel it out by putting photon on the top. And you probably know this. Guess what? 1 mole of photons contains 6.022 times 10 to the 23rd. that goes on the top. So if I do that, and I can crisscross it that way, that will now give me the energy in kilojoules per mole. This is going to become important in another later lesson. So 3.91, just for AP, 10 to the negative 18 divided by 1,000 times 6.022 exponential 23rd. It's going to be it's a very large number, 2355 kilojoules per mole. So 3.91 10 to the negative 18. I'm going to double check it. Yes. All right. So just do, so this is all you have to do. 1AB and 2AB. I thought there's something for AP, but it's going to come on another worksheet. It won't be today. It'll be another lesson. All right.